like to welcome everyone. My name is Larry Arthur with the Indiana chapter of the ACI. We're here today for a webinar on ACI 360 presented by Chris Tull. He's Indiana's very own slab consultant. He is running CRT Consulting. It's his company. He can help you out with all kinds of things. As many of you heard last week in 302, he has got a diverse knowledge of the slabs and their design, and he can help you out in anywhere you need. So today we're going to listen to him talk about 302. With that said, I'm turning it over to you, Chris. Thank you.
Thanks for having me here, guys. I appreciate you being here. So, last week talked about the construction of slabs. We'll talk a little bit about the design today, kind of a innocuous thing, and we'll talk a little bit. I'm looking at the registration. So we do have some engineers. We have some testing firm, a couple ready mix guys, many contractors, which is good. Couple fiber guys. Who else do we have in here? Yeah, even a couple architects. It looks like. So it looks like a good group of people. Maybe 95 folks. It looks like there's only 31 on, Larry, and looks like you had like 95 registrants, and about a third of those decided to be with us here today. So. So it sounds about right. So thanks for having me here today. We'll go through a couple of these items here and see what we can do. Last time you've seen this, my background is a civil engineer from Cornell. As my wife, Indiana graduate, said, she found the only damn engineer in the state that didn't go to Purdue. So that's me. Out of school, I worked for a large concrete contractor, construction manager, was in the ready mix industry for quite some time, and founded CRT Concrete Consulting in 2007. And I kind of focus on a relationship approach to some technical issues. So I'm very active in ACI, as you can see, voting member of 302 that we talked about last time, as well as 360, and do quite a bit of the ACI stuff. I am a PE in a few states. If you're an engineer, you probably think that's a good thing. If you're a contractor, you probably think that's not so good a thing. So depend on what hat I'm wearing. And I do have a lead AP, and helps me with some of the green building things. We talked a little bit about that last time. So here's my specialty areas, and certainly slab on grade is far and away my biggest business entity. Due to COVID, these big box distribution centers are crazy out of control. Hundreds and hundreds of them being built, and I'm working on projects anywhere from Miami to Seattle and California and New Jersey and kind of everywhere in between. So I do have a myriad of experience. My role on that very rarely is the engineer record. Not really something that I want to do. My services more complement the current design and construction team. So I'm not trying to get to some of the good engineers we have on the web with us today. I'm not trying to get into their business segment, rather than just trying to complement what they're already doing. So we're going to talk about ACI 360. Hasn't been published in quite some time. The current chair is Scott Tarr. He's working diligently to get a revision out. I've got my responsibilities as far as that goes. So we'll spend some time talking about that. But the first thing I want to talk about is ACI 318. Engineers, we love building codes. And the first thing that you need to understand if you are a designer is ACI 318. This code does not apply to design and construction of slabs on ground unless the slab transmits vertical loads or lateral forces from other portions of the structure to the soil. So we are exempt from the building code. So all you designers who try to put the 0.15% steel in the slab and get into a little bit of trouble, don't do it. So put 318 away and come back to our friends at 360. And that's where we need to be in designing concrete slabs. So if you look at the demographics of the voting members of our 360 committee, we've got a good balance between consultants, contractors, designers, general interests, and producers. So we have a very good balance there. It's a pretty good document. Some of the things in my view are a little clumsy that they're being Chairman Tarr is cleaning up, and we'll talk about some of those things as the next version comes out shortly. Here's the table of contents, and certainly in chapter 1 and 2, the same for most documents. And the things, again, kind of the same format. We're going to talk about types of slabs and make sure we understand those briefly. Talk about soil supported slabs. I think we can all agree that the support system, what we put our slabs on, all of our slabs are only as good as what we put them on. Talk about some loads, and then we'll talk about joints, and then we'll talk about some design of unreinforced slabs, and then we're going to talk about design of fully reinforced slabs for crack width control. So, and frankly, a lot of people get confused. They go to that chapter 8 and get themselves in a bit of a bind when they do that. So we'll make sure we distinguish through those. And again, I'll mention some of the changes that are coming up in the current design. So the types of slabs, unreinforced slabs, then the reinforced with deformed bars or welded wire fiber reinforcement is used to limit crack width control. What's a little confusing about the 360 is if you have shrinkage and temperature steel, light gauge mesh in your slab, you are designing an unreinforced slab. So that's been a little confusing on some things. Reinforce, continue to reinforce a 0.5%. We'll talk about that. We're not going to spend some time talking about shrinkage comp. Those are good systems. Post-tension systems out there. Steel fiber is becoming more and more common. So is synthetic fiber reinforced, macro synthetic fiber reinforced slabs. And then there's building code slabs that hold up mezzanines and stuff like that. We're not going to talk about those today. So those are the slab types that are in the document. As we move forward and talk about slab support, the ACI nomenclature is that the concrete sits on a base that sits on a sub base. If you have both, that sits on a subgrade. So most of the time, we really don't have two bases, a base and a sub base. Here in Indiana, we might have a slab that sits on some 53 stone. So that works pretty well. And more and more often, we're having a vapor retarder in the slab. But if we talk about the design criteria, the Modulus of subgrade reaction, you know, what is that? It's modeled to be a spring constant, like our slab sitting on some springs. Do we test for that? No, we don't really test for that. We kind of have some soil properties that have associated typical Modulus of subgrade reaction. K value of 100 PCI or PSI per inch is kind of common. Not too big on what the value is. I'm just more concerned that we have uniform support under our slabs, that we don't have a lot of running, and as we go through that. So vapor retarder, we talked last time in 302 that vapor retarders are becoming more and more prevalent. In my view, I think you're going to see all these warehouse slabs, the entire slab is going to be on vapor retarder. One of my biggest clients, that's their standard operation now, is that we have the concrete slab on a positive vapor retarder to take underlying moisture out of play. We do have this nomograph that you can go through, this flow chart, to find out if you do need the vapor retarder. But if you're storing any product on the slabs, and more of these DCs, they have cardboard boxes directly on the slabs. That's why we're putting the vapor retarder in there, to make sure that we take the vapor transmission from the soil out of play with a positive vapor retarder. There's some pros and cons to doing that. The old thinking was curling was more on plastic. I'm not sure that's true. Curling's more a function of moisture gradient. And I think we're choosing these sites that we passed on 20 years ago. So if you're on a wet site, which we very well may be, your moisture gradient may go down with a vapor retarder, not up. And in fact, your curling, long-term curling may be less. So notice that we do have these things. And when we have them, we're trying to put these things put the concrete right on top of the vapor retarder. So showed this slide last time, again, trying to take some out-of-state trucks, so I don't show any favoritism to all of our friends in the ready-mix business here in Indiana. But we want these trucks moving around on these sub bases with not a lot of rutting. So we're uniformly supported, that's good, and that's kind of what we need. If we look at the subbase issues, I can tell you there's some issues around the country, maybe not so much in Indiana, but expansive soils can be problematic that move around, shrink and swell with moisture content. There are some large fill sites. I'll talk about that a little bit, and how if you have a large fill site, even if you do put in your fill in compacted layers, you can have some long-term consolidation of those fills, and we need to monitor those and measure those. We don't have a lot of slope slabs here in Indiana, but if you get into northern Kentucky, I think I mentioned last time, I worked on a 1,000,000 square footer that had a whole bunch of cut and a whole bunch of fill, and they actually sloped the slab 0.5%, and the slab actually was tilted 6 feet. It was 6 feet from one end of that big sucker to the other. So that can be easily accommodated. One direction slope is not that big a deal. Can't even see it. So that's the subbase and the subbase issue. And again, we want it to be uniformly supported. We want to pick an appropriate K value. If you tell me it's a K of 150 or a K of 100, I'm not going to argue with you. Those are pretty much the same to me. If you tell me we have a K of 500, 600, I'm probably going to question that a little bit, find out how we're getting there. Do we have some sort of chemical stabilization, cement stabilization? That's a very high value, not typically see. So that's it on subbase. And Larry's kind of monitoring the chat box. If you have any questions, you can put them in the chat box, and I'll try to address them as we go. If we took a look at the loads, we got a bunch of different loads that we can have on these slabs, and we want to mention the vehicle loads, concentrated loads, line loads, construction loads. That's interesting. Construction loads, not something too well thought out, and I have a couple examples that I can share with you on how construction loads can get you into a bind. Environmental loads, these are shrinkage and warping. Thermal loads can be significant on some of these slabs, so we'll chat about those a little bit. So what are the loads? Do we know them? Do we know the loads? If we're building 750,000 square foot out in Plainfield, do we know the loads that are going in there? We may not. Do you design that slab? I don't know. Most of the time in Indiana, these warehouse slabs, they're 7 inches yesterday, they're going to be 7 inches today, and they're 7 inches tomorrow. Not a lot of thought gone into some of these, kind of a clear height thing. If the building's this height, we're going to have a 7-inch slab. So the thickness does depend on the loads. And if we talk about these different loads, we look at some of these fork trucks, and if you measure some of the, these things aren't too bad. When you measure the contact area of these pneumatic tires, not too bad. But if you get into some of these pallet jacks, where you see that we might have a half inch contact area across 5 inches of a very hard plastic wheel, these things with some big loads can play hell on some joints. So we're getting these fork trucks that go faster and faster. They carry more and more weight. They have more and more harder and harder wheels that they can create some durability issues on joints and slabs. So we got to understand those things. We have uniformly distributed loads. So this is a project that I worked on down in Tull City. The owner of this facility was under the belief that when these brake discs fell over, these 1, 2, 3, what are these got here? 1, 2, 3, 4, 5 pallets high, a whole row of this stuff fell over and it chipped the slab, and he did not think that his slab should chip simply because these cast iron brake discs hit the floor, that they shouldn't chip the floor, but they did. So you can have some uniformly distributed loads there, and if you look at some of that, you might have some tension in the bottom of the slab in between these loads, and you can have tension in the top of the slab in between these loads. So you got to check and see the loads and what you have on each portion. If you have too much tension in the bottom and you get a crack here, no one's really going to complain because you can't see it. But if you get something in between here, then that could be something that you have to deal with. So there's the thickness, and then we have our K value resisting these loads, and then we have the concrete properties, modulus of rupture, modulus of elasticity. find it very interesting that the whole slab design is based on the flexural strength of the concrete. Modulus of rupture, very rarely are we making beams. I'm a big fan of molding beams on slab placements. I know they're expensive. I know they're difficult to handle. But what typically what I see is that we kind of have a default thickness, pick a number, 6, 7, 8 inches. Then when the developer gets a tenant, they might want to come in there and rack it, and someone will ask the engineer record, hey, can we handle these rack loads? And when we go to calculate these things, we're using the modulus of rupture, the flexural strength of the concrete. If we don't have it, then we take an educated guess, and being engineers, we typically guess low. So I'm a big fan of certainly monitoring the concrete strength with some compressive cylinders. And then I kind of throw out there that on my jobs that I prefer to have one set of beams per slab placement and have that set of beams taken from the same loads of one of the previously mentioned sets of cylinders. So we can kind of make a correlation between compressive and flexural strength, and we can have that information. So if we do have a big post or a racking or a mez going in on the slab, then we'll have a little better information when we do some design. So there's the loads. We could have a single post that can create some tension in the bottom of the slab. And then we have these rack loads that go in here. These are becoming more and more common. Never met a rack manufacturer that said the slab couldn't handle the racks. We'll talk a little bit about that. But racking loads are certainly getting to be more and more common. So if you look at some of these rack loads, we can have some tension underneath the post. We can have some negative moment top of slab tension in between the racks, and we can even have some tension under the racks at the top of the slab, depending if you're putting product on the slab or not. So these are some typical loads that are gone, and these are kind of what some developers would go with and say, hey, this is what my slab can handle based on these loads, and they kind of go through there, and we'll talk about kind of design as we work our way through. So those are typical loads that go there. 360 does have some typical factor of safeties, moving wheels that 1.7 to 2, and if it's commonly used, you can read that. Those are different factors of safety. Kind of 2.0 is the upper limit on that. So if you have line loads or other structural entities, you got to go back to the code. But these are just for soil supported slabs. So some typical factors of safety that are used. So I do want to mention something called a stress ratio and how that can be used. PCA created these design activities for fatigue, and you kind of, depending on the stress ratios, how many repetitions that you can take. So say that you take the stresses in the slab divided by the capacity. So if we had 455 psi of stress and we had a capacity of 650, we'd have a stress ratio of 0.7 or a factor of safety of 1 over that of 1.43. So if we have a 0.7, then if you go to the design curve, then you can have 100 repetitions of that kind of load. There you go, stress ratio of 0.7. So any question on the loads, on some of those loads come in, Larry? Any questions? No? All right. I got to look and see if I can see the chat room. I don't know if I can. Yeah, I can. All right, I'll leave that up. So environmental loads, as we talk about some of the environmental loads, curling and warping can be an environmental load. I've done some finite element work on this kind of stuff, and what's interesting, so say you've got 700 flex slab, which is kind of typical here in Indiana, that you might use 250 psi of that capacity simply to support the curled slab. So it eats away to the capacity of the slab, and so that's something that you need to be aware of. We can reduce curling by saw cutting. We talk about that. We can reduce curling and shrinkage and curling by mix design. We talked about that last time. So I think the industry is doing a pretty good job of doing that. I don't think we really understand curl as well as we could, but we kind of manage curl by having higher factor safeties, and we get away with some loads without having too terribly many problems. So I don't see anything in the chat room, so I'm going to move on and talk to joints. But before I do, oftentimes the designer does not have the load. And again, that the developer and the marketplace dictates thickness. This big box slab business is an interesting business that the only market segment I've been involved that no one wants to differentiate themselves. They all want to kind of be the same and compete in the same space. So when someone says, "Hey, can everyone thinks this should be a 7-inch slab? Can it be 6?" And then I say, "Well, what are the loads?" And they say, "Well, I don't know." And then I say, "Well, then I can't help you. If I don't know the loads, I can't really tell." Now, I can calculate the capacity of a 6-inch slab, and you can communicate that to somebody and say, "Yeah, we'll build you 6, and this is what you can put on it." But having these loads, particularly on a spec building, is something that are not readily available. So if we move on to joints, so let's talk about joints. I do a fair amount of troubleshooting as far as slab consulting is concerned. And very rarely am I taught looking at cracks in the middle of a slab. I'm always looking at problems at joints. So jointing is something that needs to be designed, and it needs to be designed properly. So we have isolation joints that keep things that are moving away from things that do not. 360 has some column isolations in here, and I am a big fan of simply just wrapping columns, particularly these HSS columns, wrapping them with foam expansion joint material and pouring right to them. I will say that we do want to make sure that we don't have the anchor bolts from the base plate up into the slab, that we want to have our slab to move independently of these columns. We saw cut right to the column. It works real well. I've got some markets that say if you do not pinwheel, you will get cracks off of the square HSS columns. Here in Indiana, we typically do not pinwheel. We saw cut right to the middle of the column and don't seem to have a lot of problems with that. You can do diamond isolations if you like to. I'm a big fan of the diamond isolations because you're going to build those things. The slab's going to curl, and the owner's going to call me out there and say, "Hey, my building's sinking, my columns are sinking." When in fact, columns aren't sinking, the slab's just curling up a little bit around the isolation. So don't like to do those. We do isolate maybe some wind bracing columns, some things like that. I'm a big fan of round or hockey rink shape if we need to have some isolation. So these things are done, but again, if we don't have to have isolations, a much cleaner look. So that has to be said. I like to have joint expansion joint material between the slab and some walls. If we're doing that, I think that's important to do to allow for some movement. So it doesn't necessarily need to be a 1/2 inch, could be a 1/4 inch, but I would rather not have the slab sticking to the walls. Keyways are no longer recommended. We're not doing keyways anymore, so we're not doing those things anymore. So please don't do keyways. Don't do keyways with dowels through them. Don't do keyways with tie bars through them. Save your keyways for something else. Actually, I'll take that back. Don't save your keyways for something else. Don't use keyways. Don't use them in pavements. Don't use them in slabs. We're not doing keyways anymore. So what is very clear in ACI 360, and a lot of engineers and contractors get bit in this, is if you have rocking slabs. So this is very clear in 360. It's been quoted in court cases quite a bit. When the designer cannot be sure of positive long-term shear transfer at the joints through aggregate interlock, then positive load transfer devices should be used in all joints subject to wheel traffic. So what does that mean? Is if you don't think you can have aggregate interlock, and if you have unreinforced slab, you probably don't have aggregate interlock. then you should have positive load transfer. Well, what does that mean? That probably means dowel basket. Dowel baskets are very, very expensive. So what I do in my business is what I try to do is educate the owner and say, hey, this is what ACI says about load transfer. And if having a couple panels rocking around a little bit is going to be a big issue for you, then we need to talk about dowel baskets. Well, what do dowel baskets cost? Well, they might be $250,000. Oh, well, what if I have a couple panels rocking around? Well, we can go in there and seal the joints, or we can under seal these rocking panels. What's that cost? You might have 20 grand in that on an isolated instance. So I can skip the 250 and I might have to do the 20. Yeah. Well, that sounds like a better business decision. That's fine with me. It's just my job to educate you and make sure you understand what may or may not happen with that slab. So we have different types of load transfer. We've got the diamond dowels, plate dowels, square dowels, round dowels. We can get all these different things in baskets and use them as we need to use them. The plate dowel has been certainly the most common. I like the plate dowel because it can allow for 2 degrees of movement, where round dowels generally only have one degree of movement. So these are figures right out of the current ACI 360 document. So again, typically what I see in the slabs is almost always, or maybe always, we have load transfer at construction joints. Typically they're plate dowels these days. Do we have load transfer at contraction joints or the saw cut? We might have some sort of load transfer in the speed bay, but in the rest of the slab, typically not. It's typically unreinforced slab throughout the slab. And then we have that conversation on, if we do have some rocking panels, what maybe we had to do to address that. So buried deep in the joint chapter is this notion of enhanced aggregate interlock. And enhanced aggregate interlock is running a small amount of steel through the saw cuts and having that steel hold those joints together and getting some aggregate interlock. So this is happening more and more. I'm a big fan of this, and particularly in the speed base. What I typically see is the engineer of record needs to have some sort of steel in the slab along the perimeter of the building, particularly at the low footings or the dock walls, the tall walls, to create enough dead load from the slab to handle some thermal bowing stresses in either his tilt panels or his precast panel. I like to take that same steel that's creating a dead load situation and create enhanced aggregate interlock, particularly at the speed bay. So we're seeing this more and more. I'm a fan of some Bigfoot mesh. This is some picture of the Bigfoot mesh. So this is a modified construction joint detail that we can talk about here in a little bit. So this way we can have enhanced aggregate interlock by running this Bigfoot mesh through the joints. The reason I like this Bigfoot stuff, it's like a D 7.3 by 16 by 16. It stays where you want to have it. You brick it up or you chair it up, it stays where you want it. The 2.9, even the 2.9 bows in between the supports. So that's something that we need to be aware of. Here's a vapor retarder. The one thing you do need to be aware of, when you do use this, system of enhanced aggregate interlock, that the joints stay tighter. So what you'll find is you might have more movement at your construction joints, and you can have what is called a dominant joint. This is a dominant joint in a concrete out in California, and all the construction joints on these things opened up a 1/2 inch. So what we're done is modified the construction joint detail. This is the diamond dowels 18 on center. We run a mild, about 0.1% number 3 bar through there, and we kind of slightly tie that joint together to keep those construction joints from opening up, so we don't have these large dominant joints in the slab. And there's a picture of that modified construction joint detail, a little sketch that you can steal shamelessly and use as you like. So that's the joints, and if you go with these contraction joints or joint spacing rules of thumb, you're gonna be in a low curl situation, and if you have a 6-inch or greater floor, joint that baby 15 feet on center. If you had 50, if you had some sort of weird spacing like 62 feet, I wouldn't cut it up. If you had to do 16 feet or 15.8, there's kind of a guideline on that. But if you go by these rules of thumb, you'll be in good shape. Make sure you saw deep enough. Watch your aspect ratio. If you do these kind of things, it's really effective in minimizing, not eliminating curl problems. But so if we've got some 0.1% in the speed bay where the fork trucks are running up and down, we got some sort of Hansen aggregate interlock load transfer, and the rest of the building, it seems to work out pretty well here, certainly in central Indiana. So keep that in mind as you design that thing. Now, oftentimes, this is where the designer kind of gets hung up a little bit. The thickness is kind of easy. We're kind of guessing on it anyway, or the market determines the thickness. It's how these joints are done and how these details are done and how the building is tied to the precast or tilt wall panels. All those nuances is kind of what makes or break a successful project. How you handle the docks, all those different things is kind of makes or break a good project from a bad project. So again, be careful when you tie into the foundation or the walls. And really what I like to do is I like that slab to float, kind of move around, let that slab move independently from other objects. And if we can minimize restraint, we can minimize cracking. So that's kind of my philosophy. Let that slab move around a little bit. So here's a column isolation. Here's a block out. I think they look terrible. That's a polished job. I showed this last time. I think it's better than a diamond, but again, I'd like the contractor to finish those off. So everyone tells me in my pre-placement meeting that, yeah, we're going to finish those off with an angle grinder. Sometimes they do, sometimes they don't. A little bit of TLC. So you can see the elastomeric joint sealant around that HSS column and the Mastermec sealer that's over the foam, the expansion joint material. Makes a pretty clean detail. If you're doing tilt up, I'm a big fan of column sleeves. The detail ends up looking just like that rather than the blockouts. So that's that. So any questions coming up? I don't see anything in the chat room. But I will go into design if we could talk about design. So give it a minute, but I don't see anything popping up here. All right. Okay. All right. So design of unreinforced slabs. Let's talk about that. So the typical Westergaard analysis where they have 3 conditions: closer to a corner, edge loading, middle loading. Certainly something you can look at with a Westergaard analysis. PCA's got design material, design guidelines. Excuse me. Corps of Engineers does. Welded Wire Institute does as well. So if we look at on how thick that is, Scott Tarr and Jim Farney wrote the latest Concrete Slabs on Ground book. It's a pretty good book, and there's some nomographs in here that Tarr put together. And you can do some design based on this fork loading design. Notice that he's got one for edge loading and one for interior loading. No corner loading. Frankly, the corner loading is so high that you can't really afford to build a slab with corner loading. And having a true corner without any load transfer in it in a building is very rare to have that kind of loads. Corner loads are kind of in the perimeter against walls where you don't really get these bigger loads. So these are the nomographs. These are the nomographs, so you kind of figure a stress ratio, and the PCA guide walks you through that. You enter you got a stress ratio, you get your contact area, and then you go down to your wheel spacing, and then you run over and hit your K value, and you have your slab thickness. So very, very intuitive. These were built using finite element. So TAR did about 2,000 FE analyses and put these nomographs together. So some people use these things. I use them on occasion. So there's nothing wrong with that. There's a pretty hefty factor of safety built into these things. I think a factor of safety of 2 built in these things. So they generally work pretty well, but they are conservative. There's that. Let's see what we got here. Then there's also some nomographs for some rack loads and post roads. Excuse me, same kind of concept. You got some X direction, some Y direction. Then you go in there and you hit some spacing. You go over to your K value and your contact area, and you get a slab thickness. So works out pretty well there. There's some allowable random non-uniform loads. Capacity, again, you go in with your flexural strength, and you got some K value, and you can see what is the allowable load pounds per square foot that a slab can handle based on these different K values and thicknesses. Kind of a quick and dirty design tool. And I use this quite a bit as they say, hey, I've got some pallets all over the place. You do some weight on that sucker, and then you can kind of get an idea of what your slab needs to be. So that's a very good guide. That PCA guide's good. Welded Wire Institute's got some design methodology. I would caution you in using the subgrade drag theory and get those joints extended too far out. So some of the mesh guys say, hey, you put the steel in there, you can extend the joints. Not a big fan of that. I stick to that 6-inch thick or 15-foot joint spacing. I stick with that pretty well. All these design methodologies kind of come down to the same thing. More and more common these days is finite element analysis. I'm going to talk a little bit about this today, and talk about how you can model curling and warping. I do that, and you can compute stresses on the top of the slab and the bottom of the slab, and then talk about factor of safety and kind of what's important to you. So here's some uniformly spread out loads, 1,000 pounds per square foot. You got a line of pallets here, a line of pallets here. You got an aisleway and another line of pallets. Those are the loads that you put in there. You put all that stuff into the finite element program, and then that you can look at the stresses. So you can see here in the top of the slab, we have a stress of 144 PSI. That's fine. In between there, we got a flexural strength there, maybe about 700. So we got a very, very low stress ratio. We're not in any danger of cracking. Then if you look at the stresses at the bottom here, 163 PSI, again, looks good. So you can model these different things and go through and look at each of these different stresses. So you might have a building with a bunch of conditions there. And then one of the conditions could be an area that has this kind of loading here. I go through and model this thing, look at the stresses, and you do an assumption on thickness and that's how you model this thing. Now in this analysis, I modeled it without any curling and warping. The way that the curling and warping is modeled is through a thermal change. A thermal change and the warping of a slab due to thermal would be the same as drawing. So I know how to change these temperature differences to get a certain amount of curl. I can model an 1/8 of an inch of curl or whatever we're doing, and I can model the different joint spacing and all this stuff to come up with these stresses. So that can be done with the finite element. So here's a fork truck, a 19,000 pound fork truck on 2 wheels. So we've got, in this situation, we've got a 6-inch wide wheel that's 7 inches wide for a contact area of 42 square inches. The wheels are 36 inches apart, 19,000 pounds. Put that thing on the slab, and here's the stresses on the interior. Top of the slab, hardly any stress. bottom of the slab, we got 254 PSI. So again, if you look at that and if you took that over a corner with some curl, that the load is 250 PSI, maybe the curling is another 200, you might be 450, so you're getting up near the capacity of the slab. So you can model these things with finite element. So here's a single post load. Here's the 16,000 post on a 3x4 plate. And again, top stresses, bottom stresses, you can see the things are getting higher and higher. So here is racking loads. And this is kind of a cumbersome thing here. A model I did that I said we've got some rack loads here. So here's a rack, one rack, two racks. Excuse me. I said we got a pallet on the floor, not on the rack. That's what the dark boxes are here. And then we have a fork truck in front, maybe picking it up. We can model all that there together. And again, when we look at these things, that in the top of the slab, we don't have a lot of stress, but the bottom of the slab, we do have back-to-back. These back-to-back loads are the killer. And almost always it's these back-to-back rack loads that are going to be the critical design of the slab. So if you have some very high rack loads, you can have some very high stresses. If you have very high rack loads, you can have some high stresses in between the racks. And if you exceed your modulus of rupture, you can crack the top of the slab, which is not a good thing. So I tend to have a higher factor of safety on my top of the slab stresses, negative moment or negative stresses there, because I don't want to have a crack on the slab. It's a perceived defect. So again, a good way to model some of these stresses that can be done. Some of these FE tools, the one I use is Everfee. It's free. It's kind of a pain to deal with, but some of these a lot of the structural engineers have these finite element tools that they use quite a bit. So a lot of these have designed in factors of safety. So again, I'm a higher factor of safety on where I can see cracks than I am where I don't see cracks. So a couple of guidelines that I'd like to throw out that I've learned over the years is that two people you cannot allow to determine your slab thickness. I'll start with the second one. You cannot let your rack guy determine your slab thickness. These rack guys, they'll say, my racks can hold 20 million pounds. Okay, and I'm going to design a slab. Now it's going to be 14 inches thick. All right, well, is anybody gonna build a 14-inch thick slab? No. Are you going to use the full capacity of your rack? Probably not. So what I like to start with is a pallet weight. How much does the pallet weigh? Okay, I know the pallet weight. How tall is the building? All right, I know how tall the building is. So you're physically limited of how many of these pallets can be stored on the rack. Therefore, you have your rack loads. And that's kind of how I like to do the rack loads is by the pallet weight and the height of the building to come up with some reasonable rack loads. So if you let the rack load determine that, you're going to be way too thick. And again, the fork truck, they'll say, hey, my truck is capable of holding 10,000 pounds. All right, but I'm only picking up two 500-pound pallets. That's a whole different loading environment. So we kind of got to work through those issues. If you design to the capacity of the racks and or the capacity of the fork trucks in the building, that you're likely going to be way too thick, way too conservative. And again, the concrete and cement industry will thank you, as they'll have some very beefy slabs. So definitely the racks do control. Back to back is where you start, and that's going to probably be your controlling entity on the slab. Any questions on design of unreinforced slabs? I don't see anything in the chat room. I don't know, Larry, are you still with us here?
Yes, we've got one question from Steve Spitzer. He wants to know what software you're using for your examples.
Everfee. It was made, and I'll go back. It's made by the University of Maine. and it's based on highway. So if you see it says wheels, and so what I do is I fake this in to be a base plate and or different kind of loads, but it's somewhat limiting. I can only put the load in kips. So if you tell me it's if it's 7,500 pounds, I put it in 8 kips. But it seems to get the job done. I know there's different finite element programs. Some of them are costly. Some of the structural engineer guys have these FE programs to design their frames, steel or concrete frames. And so they have that resource to do the slab design if they'd like to as well. I'm too cheap to spend 10 grand. For the limited amount of slab stuff I do, this Everfeed seems to work pretty well for me. All right. One thing again, I want to talk about design for reinforced slab for crack width control. If you want to design the slab for crack width, so you want to have very tight cracks that you are going to be at 0.5%. So you're going to load that sucker with steel. You're going to get the steel near the top of the slab, and you're not going to joint it. You're not going to joint it. So that's something that a lot of people get confused. Is they'll go to that chapter in ACI 360 and they'll put in 0.5%, and then they'll try to do control joints and it doesn't work, and they get out of joint cracking and they don't know what's going on. So in the next edition of ACI 360, we are gonna have a chapter entitled Design of Lightly Reinforced Slabs for Enhanced Aggregate Interlock. All the information will be the same, but it'll be a chapter entitled for doing that work. So right now in 360, you do your design in the unreinforced design slab methodology, and then you go to the joint section to find this 0.1%. It's very cumbersome. I know where it is because I'm on the committee, but if you're not on the committee, you're likely not going to find it. So that's going to change. So this is not a bad design. One of the guys on the web here today is doing this. Is that there's a highly reinforced slab that has to be tied into a pit. So he changed gears and said, well, if I've got to have all that reinforcing because of a pit, I'm just going to reinforce that section of the slab, not going to join it, and let those things crack and have tight functional cracks in the slab. It's a solid design strategy. Now listen, tell somebody that you're not going to join it and that you're going to crack it and they're going to be tight cracks. This kind of design methodology also works well with steel fiber reinforced slabs or high volume macro reinforced slabs. That could be the design strategy, that we're going to have very, very tight cracks that are very, very functional because we have positive load transfer across the cracks. Works fine. Just got to communicate that with your client and or your tenant. So that's that thing there. So that's one chapter that's going to be added to ACI 360 is the design of lightly reinforced slabs for enhanced aggregate interlock. The other chapter that's going to be added is extended joints. Extended joint slabs are becoming more and more common. A couple brand names out there that are common. They're kind of proprietary. There are jobs that come that you see on the plans. It's just a giant box that, slab designed by contractor. That's fine. They're proprietary. What I would tell you is, in my experience, that the extended joint slabs can be good. I happen to know Scott Metzger with Metzger McGuire, who sells MM80 joint filler. And there's one slab system, extended joint system out there that he sells as much joint filler in the joints just at the saw cuts than if we were cutting them up in quarters, that the joints open up that much. So you got to design for these dominant joints. You got to understand the dominant joints and be ready to fill the dominant joints if you need to. That's something. Certainly, if you have tapered dowels and you have joint openings of a 1/2 inch, 3/4 inch, then you can have a reduction of load transfer. Then you might want to try to understand that as well. Those are the things that you need to talk about. Furthermore, a lot of these extended joint systems have got a pretty good handle on managing shrinkage. So either they're eliminating shrinkage, a shrinkage comp floor, something like that is certainly eliminating shrinkage, or a lot of these systems postpone shrinkage until those shrinkage stresses develop later on in the slab's life when it has more strength in order to handle these inhibit these oncoming shrinkage stresses. So those systems are handling pretty good. What they don't have a handle on, and I would caution everybody, is the thermal stresses. So if you have an extended joint system and you're delaying the shrinkage through some sort of admixture or whatever you're doing, I'm not a big fan of doing those things outside. So I like to have the building up, the precast building up, so I don't have these huge thermal changes. Not so much now, but say maybe late March, early April. Is everybody losing audio? Or is that just one folk? My audio all right, Larry?
Yeah, it's fine on this end. I've got it.
Okay, good. Make sure you have a handle on those thermal stresses. I'm not a big fan of building these extended joints outside, like in a tilt-up environment. If you're in March, late March, early April, you might be 35 degrees in the morning, and 4 or 5 hours later, you could be 65 degrees. And some of these systems don't handle these thermal changes as well as some of the others. So I'm not telling you I'm an expert on the stresses created by thermal. I'm going to tell you there's not many people who are. I don't think it's very well understood. But when you're jointing just at the column lines or every other column line, when you have 150 feet or 100 feet of concrete, those thermal stresses can be significant and they can result in cracking. So be aware with those. So as I kind of wind up, I want to kind of share some issues that I'm seeing in the market. Is again on these big fill sites. Careful of your K value and careful of your long-term consolidation. So this is a job that I worked on in South Bend, a troubleshooting job, and I would walk down the middle of the aisle, and we had a crack. We had a crack down the middle of every one of these aisles, and a couple of the aisles we didn't have cracking, and I'm there a couple hours and looking, and I finally figured it out. So there's the crack in the middle of the aisle. And I started talking to the people, and they go, "Yeah, oh yeah, this was a 10-foot of fill, and we put that fill in there, and we started building on it right away." And what was happening, we had some pretty large loads here, we have some negative moment here, and we got some crack there. But there were some aisles that weren't cracked. So look at this. This one wasn't cracked, but there was a joint in it. And then you put the level on it, and you got a teeter-totter. So it is cracked. It's doing the same thing. It's just that we put a joint there and didn't have the crack down there. So again, be careful on these big fill sites. Be careful on these elevated K values and what you're using on some of these things, because you don't want to get into some consolidation heavy loads that are pushing the slab down here, having negative moment on the top of the slab. So careful of that. And also, be careful in some design consistency, precast slabs and slab connections, dowels or no dowels. I've had 3 or 4 or 5 jobs where the engineer of record is saying, "Hey, I need mesh in the steel. I need welded wire fabric in the slab to create enough dead load to handle the thermal bowing stresses of the slab." And then I've got a developer who says, "Thou shalt put baskets in the concrete," and no one's communicating. So what, I show up at 3 in the morning and there's welded wire mesh going over the baskets. And I don't think that's a good idea. That's quite a bit of restraint. So we got to have some communication and make sure that we understand what we're doing. So this has happened to me in Chicago. It's happened in Indianapolis. It's happened in California, that we get a lot of these developers or tenants that are saying, hey, you got to have baskets. And then again, the engineer of record says, hey, I need that steel, and we're getting both. So what I like to do in this situation is that I'll put if they say you got to have baskets inside away from the speed bay, that we could put the baskets at the saw cuts, they work fine. I'd rather take this 2.9, flip it over to some of that heavy deformed 16 by 16 opening and get enhanced aggregate interlock in the speed bay. So we've got the mesh that's used for enhanced aggregate interlock in the speed bay. It's providing the dead load to handle the bowing stresses in the wall. We get dual use out of that mesh. Again, we take the baskets, put them in the unreinforced the slab, and get what we need. So with that, that's all I've got to present to you. I'm certainly willing to answer any questions that any of you guys may have.
Chris, thank you. Opening it up to questions.
That's why I think, you know, if you do these things in person, then you tend to get questions. The webinars, you guys are checking your email, you're doing what you're doing. So I know a lot of you want PDHs, and I think, Larry, you're going to send those over.
Yep.
Yep. And I'd like to have one for both of those too, if you don't mind.
Okay. Yep.
Yeah. I didn't understand. I'm a residential engineer and call it out all the time. All right, I see that, Eve, on the residential. So the residential, the code might require you to put the mesh in there. I don't know. What I see in the residential is usually 1.6. Don't know that it does anything to the slab, but so I don't, you wouldn't have dowel baskets in a residential slab. I don't think you're going to have a problem with that in residential. Mindy, thank you for your nice comment. I see Mindy's comment there. So, all right. Don't see anything else coming in. Glad being with you. Larry's got my contact information. You know, I make a living helping good people like you. So, you know, my MO is to be part of the problem, part of the solution, not part of the problem. You know, my job is to get these slabs built. And, you know, you know, sometimes I think my fees are a lot, but in the scope of these giant slabs, they're really not that much. So would be welcome to have the opportunity to work with any of you designers, general contractors, I'm here to help.
Chris, we do have one last question. John Krupski would like to know, what extended joint slab system do you believe works best to address the objective of minimizing joints in the slab?
Well, that's a loaded question. So I'm not comfortable in saying what I prefer. There are a lot of systems. I do think some are better than others. Frankly, I'm in favor in the extended joint systems that have some sort of expansive component, because the dominant joints can be a real pain in the butt. I gave a talk at World of Concrete. It wasn't 19, it was in 19, not 20 because of COVID. And a developer stood up and said, you know what? He goes, I'd rather have 10 miles of tight joints than 2 miles of half-inch joints. And I think that's generally the consensus on some of this stuff. So that would be my pick, is that I would have an extended joint system that would not have these dominant joint problems. There is one system out there that I've looked at. It's not extended joints, it's jointless, and it has got an expansive component, high volume steel fiber, and it is a hell of a floor. I have measured that sucker years after their placement. They don't move around. It's a fantastic floor. Next question's on keyways. Keyways have fallen out of favor because of, if I can show you, get back to it real quick. They tend to break. All right. So what I see on the keyways is this. If I can draw on here, yeah, I think I can. This will break. If you get a lot of a lot of movement in there, that piece will break off. So not a big keyway guy. Plate dowels work good. You have a 5-inch slab and you want something at the construction joint, you can use a 1/4-inch diamond dowel, works real well.
Well, I don't see any more questions coming up. Chris, I want to say thank you. It's a pleasure to have you speak for us. I'd like to, invite you back anytime you want to speak. We're going to be doing these quite a bit coming up in the near future. So it's a pleasure, sir.
All right. Well, enjoyed being with you guys. If I can do anything for you, let me know. And you guys all have a good day. Take care.
Thank you, sir. Have a great day.
Thanks.